Richard James will continue ratios and variations tutorials with ratios and variations part 3. The problem that we have here requires that we take the plan of a garden which is drawn to a scale of 1 to 20 and make calculations as further stipulated. In the previous tutorial, we demonstrated how to use the scale of a map to do a conversion, and also how to use an equation that relates units of length to convert between units. And of course, we did that in one step. We will take that approach in solving this problem. In the previous tutorial, we demonstrated how to use the scale of a map to do a conversion and an equation that relates units of length to convert between units in one step. So we will use the scale of the map and use an equation that is used to convert between units, and that we will do in one step. We will take that approach in solving this problem. So let us go straight ahead. That is the scale that is given for us to use and make the calculations on the map. In the first part of the problem, we need to determine the length of a path that is given as 13 meters, and that is 13 meters in actuality, and we are required to use that scale and convert to measurement or distance on the map, and that on the map should be given in centimeters. So there we have, that represents the actual and that represents the measurement on the map. That 13 that is given to us is actually 13 meters, and that 13 meters should be converted to distance in centimeters on the map. The path is actually 13 meters long. We need to convert that to length on the map. In this scale, the figure on the map side is smaller. We therefore need to divide by 20. So this is the actual. Notice that the number on the actual side is larger than the number on the side relating to the map. Therefore, if we are converting distance in actuality to a particular distance on the map, we will need to get a smaller number, and that we will do by dividing, and we will divide there by 20. Finally, we need to convert from meter to centimeter, because we have not done any unit conversion yet. So this 13 that we had here, 13 is in meters, and when we divide by 20, the distance is still in meters, although it is now the distance on the map. So finally, we need to convert from meter to centimeter using 100 centimeters is equal to 1 meter. We need to multiply because the number of centimeters will be larger when compared to the number of meters in the equation. So what we have here is still in meters, but we need to convert to centimeters. Notice that we have the number accompanying centimeters is larger than the number accompanying meter. Therefore, if we are converting from meter to centimeters, then the number of centimeters that we get should be larger. Therefore, by using the conversion factor, we need to multiply, or by making use of this conversion equation, we need to multiply by 100. There it is. And what do we get? Dividing by 2 is the same as multiplying by 5. Well, not exactly the same, but they are related. 13/5 is 65. Therefore, we are sure that we will get something or some answer related to 65. So there we have it. Related to 65. Actually, 65 centimeters. Let us take a look at the fraction that we used in converting actual length in meter to length in centimeter on the map. And why are we taking a look at it? We are taking a look at it because we intend to use it in the solution of the other part of the problem. Expressing your answer in square meters, calculate the area of a pond which is represented on the map by an area of 125 centimeters squared. So, express your answer in square meters, calculate the area of a pond which is represented on the map by an area of 125 centimeters squared. But we are making use of this fraction that was used in converting length in actuality to length on the map. Now, what we need to do is convert from the map to actuality. And we have discussed that before, that if we are taking an opposite step, then we will do the opposite operation. And we have also discussed that one way that we may achieve that is by reciprocating the fraction that was used in the opposite conversion. So we are converting on this occasion from the map to actuality. Therefore, we will make use of the fraction that was used to convert from actual to the map, and we will take the reciprocal of that fraction. If we were doing the reverse process, that is, converting length in centimeter on the map to actual length in meter, then we would have used the reciprocal of the fraction. So if we were doing the reverse, or the exact reverse, it is somewhat related to the reverse, as we will see in a few seconds. But what we are saying here is that if we were just converting length on the map to length in actuality, all we would do is just find the reciprocal of that fraction. However, we are not just converting length, we are converting areas. Recall that when we are converting between areas, we need to square the scale factor. So we will square the scale factor because what we are converting is area. So, as a little summary, first of all, we used a fraction to convert length in actuality to length on the plan. Therefore, to convert from length on the plan to actual length, we would do the reciprocal of that fraction, and that we have done. However, we are not converting mere length, we are converting area. And we know that when we convert areas, that we use the square of the scale factor, and that is what we have right there. So we will use the square of the reciprocal of the fraction that we did before. The area that we are converting is 125 centimeters squared. Also, we are making use of the fact that when we square 100, we get 10,000, and when we square 20, we get 400. So there it is. So we are actually multiplying 125 by 400, and we are also dividing by 10,000. And this is quite an easy mental operation. We may eliminate the zeros here, 2 of them. Then we will say 4 times 125 is 500. However, remember that we are dividing, but 2 of these zeros are eliminated, therefore we are dividing by 100. So 500 divided by 100, and that is equal to 5. So 5 meters squared. In this particular problem, which is number 15, all we are doing is using the scale of a map that we have right there to convert the distance between 2 points on the map. And the distance between the 2 points on the map is given as 36 centimeters. And we have gone through a lot of processes and methods that we may use in order to make our calculations. Therefore, we will not beat around the bush and carry on and carry all the way around anymore. We will just go straight ahead and do our calculation in one step. So we take the 36 centimeters that we have on the map, and what do we do with it? Well, we imagine that we will convert it to distance in actuality, and we know that that being the case, the actual distance will be more. Therefore, we will multiply by that 25,000. As usual, we will use the scale to find the actual distance in centimeters, because when we just use the scale of the map, the units do not change. Therefore, all we do is take that 36 that we have there, multiply by 25,000, and that 36 is in centimeters. So when we multiply by 25,000, the answer will also be in centimeters. So whatever that product turns out to be, it will be in centimeters. So, as usual, we will use the scale to find the actual distance in centimeters. We are converting from the map to actuality, from the small number in the scale to the large number in the scale. We will multiply by 25,000 as we have it right here. Multiplying by 25,000. Now, our distance is still in centimeters, and we need to convert to kilometers. So use our popular equation, 100,000 centimeters equal to 1 kilometer, to convert the distance to kilometer. We will divide by 100,000 as we have done before. So divide by 100,000 as we have done before. Now, there's an easy way to multiply by 25, which is taking a quarter and, of course, including 2 zeros. So, a quarter of 36 divided by 4 is 9. Therefore, what we will have here is 900 along with these 3 zeros. So 900,000 and we will be dividing by 100,000. So in the end we will have 9 kilometers. That calculation, you do not need a calculator to do that. And now we have our first problem, and quite likely our last problem in this section, that is based on foreign exchange. Therefore, I'll make quite a meal of it in order that everything, or most of the things that would normally discuss in foreign exchange, will be done using this single problem. Therefore, do not be amazed if it takes us close to the end of the tutorial, or it takes us to the end. So, one convenient way to represent an exchange rate is to accompany it by a table, and that is what we have in this solution here. So we will do that. So we have US dollars and Jamaican dollars, and the rate is 1 US to $3.50 Jamaican, and the table makes it plain. This first part of the problem requires that we convert 8,400 Jamaican dollars to US. So we are given 8,400 Jamaican, and we are required to convert that to its US counterpart. So there is our 8,400 Jamaican. What do we do? First, take a look at what we have there in the table. Of course, we have the exchange rate also given in the table. According to the numbers that are given in the rate, the larger one is on the Jamaican side. Conversely, the smaller one is on the US side. Therefore, in converting from Jamaican to US, the number will be made smaller. That we will do by dividing by the number in the rate. So according to what we have here, the larger number is on the Jamaican side. Therefore, when we convert to this side, we should get a smaller figure. Therefore, we will divide 8,400 by 3.5. And what is the result? That turns out to be $2,400. Consistency in the table has to be maintained. As a matter of fact, that is why we use a table. The number on the US side must always be smaller. Therefore, according to what we have here, the number over here is smaller. Therefore, if we are making a conversion in whatever amount of Jamaican to whatever amount of US, we imagine that the number that will be the result on this side will be smaller than the number that is on this side. And as we shall see later, in converting from the US side, which is the side on which we have the smaller number, if we convert to the Jamaican side, we will get a larger value. Therefore, we will multiply by 3.5, unless the rate changes, as we will see for this part of the problem, that the rate actually changes. We may treat our exchange rate as a scale in the same way that we treat the scale used to draw a map, where we have Jamaican side and we have US side. We were given 8,400 Jamaican to be converted to US equivalent. Right, so that amount of money, $8,400 Jamaican, will be converted to its US equivalent. We will also say that in converting from Jamaican to US, we are transferring from the side of greater number to the side of smaller number. We will therefore be required to divide by the rate of 3.5. So the same thing applies. Notice that we have 3.5 on this side, on the other side we have 1. So if we are transferring from this side to this side, the number that we will be required to get on this side will be smaller, being consistent with what we have here. Therefore, we will divide 8,400 by 3.5, and this is quite analogous to what we have done before. But maybe we will make another go at it, which the analogy may not be so closely related. As usual, we need to have the smaller number on this side that has the US currency. Any calculation that we make should maintain that consistency. What consistency? If we take an amount on this side, convert it to this side, then the answer should be smaller than the one that we have on this side. If we take a number from this side, convert it to the other side, then the result that we get should be larger than the one that we had on this side, based on the numbers that we have in the scale right there. In another approach to the problem, we may make use of ratios. And let us go straight ahead and do that. So we have the US and we have the Jamaican. So 1 US to $3.50 Jamaican. And we are going to ratio. Write another ratio that involves the amount in Jamaican that we are converting. And we remember that because we have done that 2 times before. So we have used the figure 2 times before, therefore we remember that it is actually 8,400. Besides, we have it right here and there. So that figure is 8,400 Jamaican. So we will write another ratio that involves that amount in Jamaican that we are converting, which is the 8,400. We do not know its US equivalent. Well, we have calculated it before, but in the context of solving the problem, it is an unknown. So we do not know its US equivalent, and we will call it X. So X to 8,400, and that is our ratio. Therefore, let us relate both ratios. The two numbers on the left-hand side are related in the same way as the numbers on the right-hand side. Therefore, if we divide the second by the first on the left-hand side, then the second by the first on the right-hand side, the results will be the same. They will be equal. So if we say X divided by 1 and 8,400 divided by 3.5, right, then whatever we get for X divided by 1 will be equal to whatever we get for 8,400 divided by 3.5. And this will be a lot plainer when we go to tutorial number 4, because anything that seems a little bit shady or uncertain, or that we are leaving a stone unturned, we will make sure that it is handled in another tutorial, and that we will do for this kind of a situation that we are saying x divided by 1 is equal to 8,400 divided by 3.5. Any number divided by 1 is equal to itself, so x over 1 is equal to x. And we will divide 8,400 by 3.5 on the third occasion, and on every single occasion it will be 2,400 if 2,400 is actually correct, and it is. So there is our answer. So we may use ratio, we may treat it as a scale, something similar to what we have used in the scale for a map, or we may use this table in which we need to maintain the consistency of the table, and therefore we will make the correct calculation all of the times. We are told that after a devaluation that the Jamaican counterpart or part was worth 70% of its original value. Then we need to calculate the new exchange rate, and we also need to do another calculation. And this problem is one of the most beautiful problems that you will ever find in CXC CSEC. And it is especially that we are living, well, I am living in Jamaica, in which the currency is not somewhat but very unstable. So this problem is very useful, and this is really a bit of mathematics with some serious and direct implication as far as our economy is concerned. So there we have the old exchange rate, and we are told that the Jamaican currency is now worth 0.7 or 70%. No problem, seeing that 70% is actually 0.7. 70% is 70 divided by 100, and we will reduce 70 by 2 places of decimal, and we will result in 0.7. So the question is, now that we know that we have that factor of 0.7 to deal with, what do we say? Well, we have no doubt that we will have that 0.7 to use. But the question is, to what and on which side? So we will ask the question, to do what? What will we do with that 0.7? And on which side? A devaluation, I realize, is not understood. I should not say that it is not understood, because as far as its practical application is concerned, students have no difficulty with it. But when they are given that in a mathematical problem, then they really make a meal of it. We want to maintain the $1 factor in the rate. The $1 is on the US side. Not wanting to interrupt it, we place 0.7 on the Jamaican side. So we are calculating a new rate of exchange. But in an exchange rate, although it does not have to be like that, but in an exchange rate, one of the currencies is always given a value of $1, and then the other one is given relative to $1 of the, usually of the stable currency, but not always. So we will have not necessarily the stable, but we are saying the stable currency on this occasion, which is the US. So we maintain that currency at a value of $1, and we compare the Jamaican to it, so we get $3.50. Now that we are doing a devaluation, we want to maintain the value of 1 on the US side. Therefore, we will have to make use of the 0.7 on the Jamaican side, for sure. But what will we do with that 0.7? So we want to maintain the $1 factor in the rate. That $1 is on the US side. Not wanting to interrupt it, we place 0.7 on the Jamaican side, and we place it on the Jamaican side without any arithmetic operator. The next question is, what do we do, multiply or divide? Some candidates may want to say multiply by 0.7 in order that we might get a smaller figure, because the problem says devalue, and devalue means that we get smaller. Like just considering numbers alone, that seems to be a simple logic. That devalue means that we are going down in value. We have the 0.7. If we multiply by 0.7 here, we will get a smaller figure, which is what devalue means. But I beg to differ, because as it relates to currency, devalue means something else. It means lower in value, maybe capability or purchasing power. But it does not necessarily mean that the figure representing it will be smaller. As a matter of fact, it does not mean that. So notice that 0.7 is less than 1. Normally, when we multiply, we have an increase, and when we divide, we have a decrease. However, when we multiply by a fraction that is less than 1, so normally when we multiply we increase, when we divide we decrease. However, when we multiply by a fraction that is less than 1, the answer is smaller than the multiplicand, and that multiplicand is a number that we are multiplying by 0.7. And when we divide by a fraction that is less than 1, the answer is greater than the dividend. And the dividend is that number that we will divide by 0.7. So when we divide by a fraction that is less than 1, the answer is larger than the number that we started off with. And when we multiply by a number that is, or a fraction that is less than 1, the answer is smaller than the number that we started with. Therefore, we are thinking that if we are devaluing, we are getting smaller. Therefore, multiplying by 0.7 is the right thing to do. And that is what I recognize that my students did. Also, it is for us to understand that when we devalue a currency, it gets weaker, and we will therefore take more of ours to buy the same amount of theirs. So if our Jamaican currency devalues, it gets weaker, and if it gets weaker or less in purchasing power, then it will take more of ours to purchase theirs. Therefore, it will take more, and if it takes more, what do we do? Multiply? No, we do not multiply by 0.7, because multiplying by a fraction that is less than 1 will result in a value that is less than the multiplicand. Therefore, we will divide by 0.7. As discussed before, it is by dividing by the fraction that is less than 1 that we will get more. Let us divide by 0.7. So throw in the division sign. 3.5 divided by 0.7. The result is 5, which is a larger number. When we devalue, it takes more of our currency. So we have more of the Jamaican currency here. It takes more to purchase theirs. So whereas we had $3.50 Jamaican purchasing the US dollar, because our currency is weaker, it will take more of ours to purchase the same amount of theirs. Like that. We have calculated the new exchange rate. Let us make note of it on this slide also. So our new exchange rate comes up as 1 US to 5 Jamaican dollars. It is for us to take the same amount obtained from the earlier conversion. So what we did was convert a given amount of Jamaican to its US counterpart, and it turned out to be $2,400. Now what we will do is, after the devaluation of the Jamaican dollar, convert that same amount of US that we got before to Jamaican currency and see what happens. We have already converted from Jamaican to US. We do not need any analysis. Remember that when we did from Jamaican to US, we divided, therefore we will multiply. So it follows, we are doing the opposite. So we have already converted from Jamaican to US. We do not need any analysis. We are performing the reverse of the process. We will therefore do the opposite of what we did before. But with the new rate, instead of multiplying by 3.5, we will multiply by 5. So the opposite that we did before was by dividing. So what we will do now is by multiplication by 5, and we arrive at $12,000. We will place both tables on the next slide and do some analysis. We will not say anything yet, although it is obvious. To some of the candidates, mathematics campers, students, it is obvious what is taking place, but we have used two tables in our calculations. Let us place them together on the next slide, and there they are. What do we notice? We realize that for the first rate, 8,400 Jamaican was converted to US 2,400. So let us highlight them. Right there, that was what was done in the first conversion. After devaluation, we took that same amount of US that we had before and converted it to Jamaican, and we realized that we got more than what we got before. And some people are saying, wow, let us therefore save in US currency, that when we are changing our money, we will get more in Jamaican. Well, the only way that will happen is if we have a devaluation of the Jamaican currency. Well, we are talking in terms of not considering the exchange rate offered by the bank. We are just neglecting that. We are neglecting the exchange rate offered by the bank right here. So we say, good, that we now have 12,000 Jamaican dollars, whereas we only had 8,400 to begin with. Well, we have more in terms of the figure that we have here, but we do not have any more in terms of its value, because its value here is the same as its value here. So the amount of the stable currency does not change. This only changed because of the fact that it lost its value and therefore will take more to purchase of the US, to purchase the US dollar. And as we see here, the amount on the US side is always the same. So we have a larger figure on the Jamaican side, but not necessarily more money. After devaluation, we took that same amount of US and converted it to Jamaican, and we realized that we got more than we got before, or we had before. Subliminally, there is a principle that the examiners are attempting to teach us in the solution of this problem. So there is a great lesson that we can learn. Notice that after devaluation, if the same amount is converted, the Jamaican is more than it was before. This follows that if we have a devaluating currency, we may use our money to purchase a stable currency. When we access our money in the stable currency, we will get more of ours, providing that there's a devaluation. The figure will be larger. But as we see here, that it is not really more powerful, because it can only still purchase 2,400 US as before, 2,400 US dollars. Notice that we said that we got more in the Jamaican currency than what we had before. As a matter of fact, only the number is greater. So only the number is greater. Remember that the currency devaluated and it took more to purchase the US counterpart. So remember that the currency devaluated and it took more to purchase the US counterpart. As a matter of fact, measured against the stable currency, we see that there is no difference. For the two transactions, the amount of the stable currency did not change. This indicates that although there is an increase in the amount of Jamaican currency, this does not mean that we have more money in terms of its purchasing power. The increase that was observed is therefore only as a result of a devaluation of the currency and nothing else. So what we have here is not necessarily more money in terms of its capability, purchasing power, or what. We are only getting more because with time the value of our money decreased, and if we measure it against a stable currency with the value of our currency decreasing, then the amount that we will take to purchase the stable currency will have to increase. There is therefore not enough benefit for saving money in an unstable currency. This is because after each devaluation, your money becomes less in value irrespective of the amount. Now that we have saved it in a stable currency, when we are ready for our money, we would have received more, which has the same amount of purchasing power that it had before the devaluation. Therefore, although it is more, it is not more valuable. However, that is better than the alternative, which is to have the same but with less purchasing power, because the currency has lost some of its value, which is called devaluation. So, although this does not mean that it is more, it is still better than the alternative, because if we chose not to save it in US and then convert in the end, what we realize is that we would have converted our money. If we, say for argument's sake, we maintained this 8,400, did not put it in US currency, but carried it all the way down here, still as our 8,400 Jamaican. If we use this exchange rate to convert it to US, we realize that the $8,400 in US would have given a smaller amount of money with the same exchange rate. Therefore, the money would have lost its value in our hand. But if we put it in the stable currency, although when we end up with a larger amount of money, it does not necessarily mean that it is more powerful in terms of its purchasing power, but it is capable of purchasing the same amount of US that we had, or the same amount of the stable currency that we had before. Therefore, we will have the same amount of money, or the same amount of value of money, but the figure would be larger. But if we had the same amount of money, which is the same 8,400, then because of the devaluation, when we convert that to US, it would have turned out to be less, and the money would have diminished in value in our hand. So it is always better to save in a stable currency. Now here we have a very nice problem. And the problem that we have there is making use of proportionate relationships. The journey to a town along Route A takes 3 hours by bus and 1 hour 20 minutes by car. The journey along Route B takes 1 hour and 12 minutes by car, and we cannot tell as yet how long it will take by bus. But what do we know, or what we do know, is that the bus travels at the same rate on both routes, and the car travels at the same rate on both routes. So let us put some of the detail of the information in a tabular form. So let us place the information given in the problem in tabular form in order to facilitate the association between types of vehicle and the time taken. We have bus and we have car. There we have it, bus, car. We have routes A and B. Right. Therefore, if a figure comes right here, we know that it is in relation to the time that the bus takes on Route B. And right here will be the time that the car takes on Route A. So Route A takes 3 hours by bus. So by bus, Route A, 3 hours. Right. Alternatively, it takes 1 hour and 20 minutes by car. Car, Route A, 1 hour and 20 minutes. And what do we imagine next? The journey along Route B takes 1 hour and 12 minutes by car. So we have car, Route B, 1 hour and 12 minutes. And our special friend, we do not know how long the journey along B takes by bus. We will therefore call it by the name of the common unknown, which is X. X is the common unknown, and we will call it X. So there we have, by bus, route B, we do not know, we call that X. Lovely. So we have all of the times, and they are associated with the route taken and the type of vehicle as we see in the table. What will we do next? We will now convert all of the times that are given to minutes, bearing in mind that 60 minutes is equal to 1 hour. We will multiply the number of hours by 60 and add the result to the number of minutes. Now we need to convert this time that we have there. All of these times, as a matter of fact, that we have right here, with the exception of this one. This one is unknown, therefore we do not have to fiddle with it until we are through. But we are saying here and now that the times that we have here are given in 2 units, hours and minutes, hours and minutes. Therefore, we will convert the times given to 1 unit, and we are choosing to convert to minutes. We are converting to minutes because if we convert to hours, then we will have fractions. And you know, as it is said, do not include an unnecessary fraction. Of course, if we use fractions, then it will still turn out to be the same as long as we progress in a logical and accurate way. We will now convert all of the times that are given to minutes, bearing in mind that 60 minutes is equal to 1 hour. Bearing in mind that 60 minutes is equal to 1 hour, we will multiply the number of hours by 60 and add the result to the number of minutes. Go straight ahead. The first one, what do we have? 3 hours times 60. No minute. 3 times 60 is 180. When we add 0 to that, we end up with 180. That goes here and down here. There. So we are converting to minutes. What do we do next? Let's go. 1 hour and 20 minutes. 60 times 1 hour plus 20. 60 multiplied by 1 is 60. 60 plus 20, and that is equal to 80. Will go here also, right there. And finally, we have 1 hour and 12 minutes. 1 hour, 60 multiplied by 1 is 60, and we need to add that 12 to it. 72 will go there, and we have it right here. And our new table of times will give our times in minutes. The bus travels at the same rate on both routes, and the car travels at the same rate on both routes. Therefore, the times that the bus and the car travel on A are related to each other in the same way as the times that they both travel on B. Therefore, there is a mathematical factor that relates the time of the bus and the car on route A, and that factor is equal to the factor that relates the time taken for the bus and the car on route B. So we are saying, and it is irrespective of how we take it, that if we are taking it this way, that there's a factor that relates this number to this one. And whatever factor that is, it also relates this one to this one. And if we take a look at it in the other way, there's a factor that relates this one to this one. And in the same way that these two are related, this one to this one is also related to this one. For A, if we divide the time taken by the bus by the time taken by the car, then we will get the same result if we do the same for B. So if we say this divided by 80, then we say X divided by 72. 180 divided by 80 will give the same result as X divided by 72. And if we do it the other way, horizontally, it will be the same, and we will demonstrate that also. So let us go straight ahead. We may show the division of the times by throwing in two fraction bars. So one there, we are saying divide 180 by 80, divide X by 72. And we are saying that this over this is equal to this over this, as long as the rates are the same along the roots. We may equate the two fractions and write the equation with the unknown on the left hand side. Therefore, we may say that 180 divided by 80 is equal to X over 72. But we are opting to write the X on the left hand side. Therefore, we will write X over 72 is equal to 180 over 80. And that is our equation. The unknown, which is X, is divided by 72. We will therefore eliminate 72 by multiplication. Consequently, we will have 72 multiplying on the right hand side. So X is accompanied by 72. We need to eliminate this 72. It is in the divisor. Therefore, we will multiply by 72 in order to eliminate the 72 from this left hand side. But we cannot do that alone. We have to multiply the right hand side by 72 also. So multiply both sides by 72, in which event 72 will be eliminated from the left hand side, and on the right hand side we will have this fraction multiplied by 72 as we have it right there. And we will reduce by common factors of 10 and 8, and it is easy to eliminate the factor of 10 when it does exist in both numerator and denominator. We will do that by striking off zeros. Then we need to reduce by a common factor of 8. 8 into 8 is 1, and 8 into 72 is 9. So all we have now is 18 times 9. 18 times 9 is 162. And what do we know? 162 minutes may be converted to hours and minutes by taking out the greatest possible multiple of 60. So let us see now. 60 is the first multiple of 60, and then add another 60 to that. 120 is the other one, and then after 120 we add another 60, we get 180. But we only have 162. Therefore, we cannot get 3 60s out of this. So we only can get 2 60s out of 162, so which is of course 120, and this 120 is equal to 2 times 60. So we take out 120 from 162, the result is 40. So that is what we have. The result is 42. So that is what we have. The time is therefore 2 hours and 42 minutes. There. We said before that the times for the bus and the car on both routes are related by a common factor. Let us find that common factor. So we have the common factor by which, as we said, the times for the bus and the car on both routes are related by a common factor. So let us find that common factor. So if we take route A, the times for the bus and the car are related by a factor. So 180 divided by 80, we get 2.25. And we are also saying that on route B, the times for the bus and the car, well, should be related in the same way by the same factor. Right. If the answer that we got is actually correct. So 162 divided by 72 is actually equal to 2.25 also. It therefore means that the factor relating both is 2.25. But this alone does not prove that we are correct. It does not mean that we are correct. Although we are correct, but this alone does not prove it. So let us go to the next slide. Fraction bars are not normally vertical, but let us assume that they may be in the context of this problem. So fraction bars are not normally vertical, but let us say they are in the context of this problem. If the answer that we obtain is correct, then the times for the bus on both routes must be related to each other in the same way that the times for the car are related on both routes. So we are going to take it, instead of saying that for this route this and this are related, and for this route this and this are related, we will say for the bus these 2 times are related, and for the car these 2 times are related. And we put fraction bars like that in the context of this problem. So there we have 180 divided by 162. The result is 1.11, and the 1 is recurring. And we also have the same when we divide 80 by 72. This proves that the answer 162 minutes is correct. If we take the times per route, they are related in the same way. And if we take the times per vehicle, they are also related by the same factor. So irrespective of the direction in which we would have gone, we divided like this, and we got 2.25, 2.25. And we have gone in the other direction, and we would have received 1.11, 1.11. Therefore, we see that the answer is correct, because irrespective of the type of vehicle the rate proves to be the same. And irrespective of the route, the rates or the relationship also holds. Now, as we said before, the fact that when we convert from kilometers to centimeters, we get a larger figure. That does not mean that centimeters are larger than kilometers. As a matter of fact, that proves the contrary, that kilometers are larger than centimeters, to the extent that 100,000 centimeters are equal to 1 kilometer. But we promise that we'll give a visual explanation of why, for equality, the number accompanying the smaller unit is always larger. So let us demonstrate why, for equality, the number accompanying the smaller unit is always larger. Now, what do we have there? Let us say that that represents 10 millimeters. 10 millimeters. We know that 10 millimeters is also equal to 1 centimeter. So there is our 1 centimeter. Considering only the two units given, how will we represent 2 centimeters? So represent 2 centimeters. There we have 2 centimeters. If we are representing 2 centimeters and we are using only the 2 units, 2 centimeters will be 2 of these. So there we have them. And what do we know? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, till we are out of breath. So we have 20 millimeters. So that is represented by 20 millimeters. So we have 20 millimeters right there. And that is representing 2 centimeters. And that is according to what we have right here. Consider also how we will represent 30 millimeters. So there we have the 30 millimeters. And what do we know? It is represented by only 3 centimeters. Only 3 centimeters. So as we can see right there, the number of the smaller ones is larger than the number of the larger one. Notice also here we have 20 millimeters. And how many centimeters? Only 2. But here we have 30 millimeters. And how many centimeters do we have? Only 3. Therefore, we will always have more of the smaller unit and less of the larger unit if we are representing the same length. And we can take a look here. All of 10 of these small ones just for one of the large one. All of 20 of the small ones, 2 only of the large ones, and so on. We therefore see that for equality, the number that accompanies the smaller unit is larger than the one that accompanies the larger unit. If we have to strike equality, then we will have to use a lot of the smaller ones and a small number of the larger ones. Therefore, when we are taking a look at the conversion from kilometer to centimeters, the number accompanying the centimeters has to be larger because the centimeter is the smaller units. So it will take more of the smaller units to give a particular length. As a matter of fact, it will take more of those small centimeters or smaller units to represent the same distance in the larger unit. Therefore, it is precisely for that reason why, as we convert from kilometer to centimeter, number accompanying the centimeter, which is a smaller unit, turns out to be a larger number. Also, as we convert from centimeter, which is the smaller unit, to kilometer, which is the larger unit, the number accompanying the units gets smaller, because the large number accompanies the small unit, and the smaller unit, the smaller number, accompanies the larger unit for the same length. And as we said before, we have more centimeters than kilometers for the same length, and it is not because a centimeter is more than a kilometer, but as a matter of fact, it is precisely because a centimeter is that much smaller than a kilometer why it takes so much more centimeters than kilometers to represent the same length. Well, it should not come as a surprise, because the smaller the unit, the more of them it will take, and also the larger the unit, the fewer of them it will take for the same amount, or we will preferably say for the same length or for the same distance.